Welcome students, and in this video we are going to start with an example of how to deduce the canonical form. So canonical form example. So we'll do one examples of each of the elliptic, hyperbolic and parabolic. Okay, so canonical form. Now the first equation which we have is this: y square x minus x square y equals to 0, right? Now you see this is of course not a very complicated equation, but it looks more or less complicated because of this coefficients y square and x square. Okay? So first of all we have to determine, but this is a linear equation, please note this, this is a linear equation in 2 dimension. Okay, so first of all we have to identify whether what sort of equation is this. So you see here, if you remember our original equation which we were starting out with, it looks like this: a uxx plus b uxy plus c uyy, okay, plus some lower order terms, some function lower order terms of ux, uy, u and x and y. Now you have to equals to 0. Yeah, now you have to understand that the nature of this equation depends on a, b and c only. So if we really compare this with this general form, what you have is a of xy will look like only y square, b of xy will look like 0, and c of xy is nothing but minus x square. Clear? And then therefore b square minus 4ac evaluated at some point xy, for an arbitrary point xy, is given by 4x square times y square. B is 0, right? So this is definitely positive for all xy in R2. Clear? So if this is the case, then we have that the equation therefore 1 is hyperbolic. Okay, so it's an hyperbolic equation, and of course you have to understand that this is true only when x is greater than 0 and y is so, except x equals to 0, so maybe minus I wrote, right? So except x equals to 0 or y equals to 0 or both. So in the upper half plane, lower half plane, except the x is basically, if you look at each quadrant, this is always true. Okay, so 1 is hyperbolic. Now you see, we have to, how do you solve this equation? You don't have to do all this whole canonical form theory. What you need to do is you just need to remember what are the canonical characteristic equations. Characteristic equation, you remember what are the characteristic equations? Okay, so those were given by dy dx equals to minus b plus minus okay, so you remember characteristic equations. So in this, for this equation, the characteristic equations were given by this two equations you will get, right? So minus b plus minus root over b square minus 4ac by 2a, right? That was given. Now if you put it in our format, what happens? The characteristic equations which we are going to get is dy by dx equals to, first of all, x by y, okay, and dy by dx, another one, is minus y by x, right? Sorry, minus x by y. I hope this is clear. See here, b is 0, so it is essentially plus minus b square minus 4ac. Again it is 4, so it is 2x times y by 2 times a, 2 times y square. So you see, it is x by y and minus x by y. Clear? Okay, now if this is the case, therefore that will imply that the characteristic, the curves, so characteristic curves, so the characteristic curves will be given like this. So you remember phi and psi we talked about, yes? So here with our example, so phi1, we said that the solution of it is phi1 of xy equals to constant. So phi, let me put it this way. The first solution is phi of xy equals to constant and psi of xy equals to constant. Those are the two solutions which we are getting, C1 and C2, let's say, in our original equation, right? So in this case, what is phi and c? Phi is the solution of this and psi is the solution of this. Okay, so let's look at it. What is phi and psi? So in our case, it will look like this: y square minus x square by 2 equals to c1. Yeah, that's the first thing. And the second one is y square plus x square by 2 equals to c2. Okay, so we have two family of circles. So these are the family of circles. Family of circles. So this solves the characteristic equation, and these are called characteristic curves. Yes. Now the thing is this: what are so important about this? So why is this important? What we can do is we can use this to form our xi and eta. You remember the whole idea is this. This equation is in x and y, this variable. We want to change it to some xi and eta variable, right? Via a change of variable such that the Jacobian is non-zero of this change of variable. Now, if we have to do something like this, what we need to do is, once again, yes, we need to find out what xi and eta is. How do you find out? You find xi and eta using the characteristics, right? So you see, if we choose xi this and eta this, then we are done essentially. So essentially what we do is this: we will choose xi of x comma y as y square minus x square by 2, the first one. Yeah, you see, and the second one is y square plus x square by 2, that's the second one. And eta of xy we can choose to be y square plus x square by 2. Please note, this is not unique. There are other, I mean, you can of course have other xi and etas which may work, yes, but the thing is you don't know how to find those. This is the only way which we can find. Okay, so therefore if you want to find ux, it is u xi x plus u eta x, clear? And this is chain rule, yes. And how do you calculate it? It is minus x times u xi plus x times u eta, clear? Because xi x and eta x is basically x and minus x and x respectively, and uy. Okay, so this is how you solve this. Do it like this, yes. It is basically u xi with respect to xi y plus u eta and then eta y, right? It's with respect to y. Okay, so this is nothing but, and now you see u xi, if you xi y, if you just do that is y, and eta y is basically again y. So this becomes y times u xi plus y times u eta. Yes, and then you have to also find ux. See, here there is no point of finding uxy, because I just have to find uxx, uyy and just put it in our equation, right? 1. Okay, so what is u of xy? See, u of xy is nothing but ux with respect to y. So ux with respect to y. Okay, so if we do that, what happens is the whole expression looks like this: u xi x square, okay, plus 2 u xi eta x eta x plus u eta x square plus u xi x plus u eta x. Clear? So that's just chain rule of, I mean, if you are not convinced, please look at the part of chain rule in any vector calculus book. Yeah, you will find it there. So now, what is u xi? You do realize it is going to be x square. In this case, it will be, so xi x is x, so it is x square essentially. So it is x square u xi minus 2x square, once again, yeah, u xi eta plus x square u eta minus u xi plus u eta. Okay, and uyy, if you want to find out, that is going to be again similarly this similar same thing, but here the x is will be with respect to y, right? So I am just directly writing it. If it will be xi y square, so that will be y square, right? So y square u xi minus plus 2 y square u xi eta plus y square u eta eta plus u xi plus u eta. It's okay. How am I writing it? See, essentially what happens here is this whole thing, this expression, uyy will also be similar sort of expression, except that x is replaced with y. That's all. Okay. So now the thing is this: you see, you got ux and uxy and uyy, right? And also, you see, the thing is, what is our original equation? If you remember, our original equation is y squared uxx minus x squared uyy. Y squared uxx minus x squared uyy equals to 0. That's our original equation. Now see, from here you see that xi plus eta, y squared is xi plus eta. Xi plus eta is y squared. You see? Yeah? Yes, y squared. And then uxx is, sorry, this I made a mistake here. This is uxx. Huh? This uxx. Huh? Okay, so uxx is this particular form, so we put this particular form plus minus x square. Minus x square, if you put this together, it is xi minus eta, right? Minus x square, and then uyy is equals to 0. Uyy is this form, equals to 0. Is it okay? Yes. So if you put everything together, you can see that this u xi, u eta eta, all of this is going to get cancelled, right? Yes. Okay. So let me. So I want you to check this part. Check that substituting this uxx, sorry, and uyy. Okay. One has okay, u xi eta. So u xi and u eta eta, those terms won't be there. It will get cancelled. Yes. So please check this. It's not very difficult, because you see y square is with uxx. So x square y square u eta eta minus x square uyy. So minus x square y square u eta eta. So you understand that will get cancelled out. So u eta eta, u xi, those terms will get cancelled out. You are only left with u xi and eta term. So that will be nothing but eta by 2 times xi square minus eta square u xi minus eta by 2 xi square minus eta square u eta. Clear? So you see, u xi is in terms of lower order. You see, these are lower order terms. So what happens is, these actually forms, and of course this is the first canonical form. If you remember, this is the first canonical form of a hyperbolic equation. Canonical form. Okay. So what happens is, see, this equation, the original equation, there are two complicated terms in terms of x and y. Now I have the similar equation, but in a different this thing, change of variable, and the equation looks like this u of xi eta. It is in canonical form in terms of two lower order terms. Okay, right. So what happens is, right now we don't know, but later on we'll see that this makes our life much easier. So we can solve these equations much easily. Okay, right. So that is how you solve the hyperbolic equation. Now let's look at the parabolic counterpart of it. Okay, so parabolic number 2. So this is example 2, parabolic part. So let's look at this equation: x square uxx plus 2xy uxy plus y square uyy equals to 0. Yes. So what is the discriminant? The discriminant d is b square minus 4ac. B square minus 4ac. Okay. So what is a here? A is x square, b is 2xy, and c is y square. C is y square, right? So if you put all of this together, it will become 4x square y square minus 4x square y square. So it will be 0. So the discriminant is 0, right? So basically this equation is parabolic everywhere. Therefore the equation 2, just call it 2, 2 is parabolic everywhere. Is parabolic everywhere. You don't have to write. So this is 0 for all x, y in R2, right? So that is why I'm saying this is going to be parabolic everywhere. Okay. Now what are the characteristics? So how do you solve this? How do you change it to a canonical form? So we find out the characteristic equation. So therefore the characteristic equation is dy by dx, if you remember again, is b. So b plus minus root over b square minus 4ac by 2a minus b plus minus. Okay. Now the thing is this, in this case you see the discriminant, this is the discriminant part, right? That is always going to be 0. So we only get minus b by 2a. That is the only thing which you are going to get. So if you have minus b by 2a, what is my b? It is 2xy, and what is 2a? It is 2x square. So this is getting cancelled out, this getting cancelled out, it is minus y by x. That's what we have. Oh, maybe no, we formed out with this, so this will be, we will just use plus b, because we just want to do it like this. Okay, so it is b plus minus root over b square minus 4x, so it will be only y by x. Yeah, so dy by dx is only y by x. Okay, so if this is the case, then you see what happens is you can solve this equation, right? And by solving this equation, what you are going to get is the solution is going to be y equals to c times x. So this is a bunch of straight lines, right? So the characteristics are straight lines. Okay. Now what is the transformation you are going to choose? So first of all, the first transformation which we are going to choose is xi of xy, which is y by x. That's quite easy, right? Now we have to find out the other transformation. So what is the other transformation? I have to find out what eta of xy is. Okay, what is our requirement of the other transformation? See, the other transformation which we want it in such a way that xi and eta, the Jacobian of xi and eta should be non-zero. This is what we want. And what is it? It is xi x, xi y, eta x, eta y. That's the Jacobian, right? So if you calculate this thing, what is xi x here? Minus y by x square. What is xi y? It is 1 by x. So you have eta x and eta y. You need eta such that this is non-zero. Now you can see that if eta is y, let's say if I choose eta to be y, this is our choice. You can choose something else also, absolutely no issues, as long as this is non-zero. But we choose the most easy one because we want our life to be easy. Calculations becomes much easier. Okay, so if we choose eta to be 1, let's say, eta to be y, let's say. So what is eta x in this case? It is 0 and eta y is 1. So in that case, 1 second, yes. Okay, so in that case, the equation becomes minus y by x square. Clear? Okay, and I did some mistake somewhere. Eta x is minus y by x square, yes, xi x, sorry, and xi y is 1 by x, eta x is 0, eta y is 1. Okay, fine. So see, this is the case, right? Now the thing is this is 0 only when y equals to 0, right? So this is 0. So y, if y is not 0, this particular Jacobian is not 0, right? Okay, so what we are going to do is we are going to use this form for y not equals to 0. So that is where we are going to transform the whole equation. Okay, so y not equals to 0 is the open set, whatever open set that is. So basically the upper and the lower. Okay, so this is the transformation. What is this? Xi equals to y by x and eta equals to y. This is the transformation, and then the Jacobian is not 0. So you do realize this can be 0 if y is not 0. If y is 0, this can be 0. So in the region where y is not 0, this transformation works. Okay, now if with this transformation what you do is this. So please look at the equation. So this I want you to check. It is very important that you know how to do this. From this earlier thing, you see, we calculated the thing ux, uy, uxx, uyy, because but with there xi and eta is given by this. Here xi and eta is given by this. So you have to check, find out what uxx is, find out what uyy is, find out what uxy is. Once you find out, you put it in this equation, and you can see that the equation 2 reduces to okay, y square u eta is going to be 0. Clear? So this is, since y is not equals to 0, we can actually write u eta is going to be 0. Yeah, for y not equals to 0. Yeah, so you see, in this region where not y is not equals to 0, right? So in that region, what is happening is this: the equation 2 is getting reduced to u eta equals to 0, right? Okay, so maybe I can do it here. See, 2 is a much complicated equation. So what we are doing is this: we are saying that for y not equals to 0, 2 reduces to u eta equals to 0. Clear? See, and if u eta equals to 0, eta equals to 0, that will imply u of as a function of psi and eta, okay, will look like so basically we want to solve it. So okay, first of all, what is u eta in this case? U eta will be a function, first of all, a function a. Okay, we have already used a, so maybe we will use some other function, pq. Okay, some function p of xi, okay, plus some constant, another constant c, okay, c1 maybe. Okay, now what is u of xi eta? Then again integrating the whole thing, you get p of xi, okay, acting at eta plus c1, okay. This is what we are going to get. So this is a harmonic equation, u eta. So if you solve it, this is what we are going to get: c1 eta plus c2. Okay, so essentially this whole thing you can write it like this. So any solution of this will look like, therefore u of xi and eta will look like some function of xi times eta plus another constant c. Okay, that's the solution. Clear? So you see this, and what is p? P is an arbitrarily twice continuously differentiable function. Okay, so this is not the end of it. Okay, now you see, therefore what is u of xy, the solution of 2, that is given by, this is basically u of xi eta, right? Xi and eta. And what is u of xi eta? It is basically p of xi times eta plus c. So what is p of xi? P of xi is nothing but p of xi is given by y by x, right? So this is p of y by x plus times eta. What is eta? Eta is nothing but y plus a constant c. So that's your solution. Where p is a twice continuous difference. So you do realize that the original equation 2 is a much complicated problem, but this equation turns out to be much easier. Yes. Okay, so last problem which we want to talk about is the elliptic counterpart of it here. So the third problem, the elliptic problem. So let's say we have this equation uxx plus x square uyy equals to 0. Clear? So we want to solve this equation, and you can see that b square minus 4ac, this is going to be minus 4x square. Clear? So that is negative, if x is not 0, of course, in that region where x is not 0, this is negative. Yeah. So what is the characteristic equation? Dy by dx, if you remember the characteristic equation, in this case this is complex, right? So it is plus minus ix. Yeah. So this also you need to check, but this is very easy to check, right? It is b plus minus b square minus 4 b square minus 4ac by 2a, right? So you just put it there. So therefore dy dx equals to this. So these are the what? These are the characteristic equations. Characteristic equations. Okay, so what I want you to do is, see, you practice some problems. What happens is, after some time you will be very clear about what's going on, so you don't have to do everything. You see, once you find out, you just have this equation, find out what sort of equation is it, elliptic, parabolic, hyperbolic. Once you do it, you find the characteristic equation. Again, this is very easy to do, right? Once you do it, you find out what are the solutions of this characteristic equation. So what are the solutions in this case? What are the solutions? You can again check. It is going to be 2y minus ix square equals to a constant c1, and 2y plus ix square, this is going to be a constant c2. Those are the solutions, are solutions of the characteristic equations, okay. So basically these are the characteristic curves, yes, and this will actually give us what xi and eta is. So what is our xi? So in this case, how do you write xi of xy? It is essentially the first expression, 2y minus ix square. And what is eta xy? Eta xy is nothing but 2y plus ix square. Clear? Now remember, these are complex variables. We don't want complex variable, we want real variable. How do you make it real? So you define alpha to be xi plus eta by 2. You remember when we talked about canonical form in the earlier video, this is how we do it. Therefore alpha equals to xi plus eta, and that is going to be a 2y, which is real. And again beta, we will choose beta to be xi minus eta by 2y, right? And if you calculate it, it is going to be minus x square. This is also real. Clear? Now you see, you have two variables, alpha of xy, one variable, it is 2y, and beta of xy, which is minus x square. Clear? And it is very easy to see that, you see, let's look at the Jacobian matrix, Jacobian matrix of alpha beta. So it is alpha x, it is 0, alpha y is 2, beta x is minus 2x, and beta y is 0. So if you calculate it, it becomes 4x, okay. And you see, x is not 0. So essentially in the positive thing, so when x is positive, x is greater than 0, this change of variable will work. This is okay. So in the region where x is positive, this change of variable will work, okay. I hope my calculation is correct. One second, let me look at it. U of x is 0, so it is alpha x, alpha y, beta x, beta y. That's the calculation, and alpha x is 0, alpha y is 2, beta x is minus 2x square, and beta y is going to be 0. So calculating it, becomes 4x, which is so sorry, I did a mistake. Okay, it is 4x. Now you see, x is given to be not 0, right? This is from the initial condition itself. So this is not 0. So Jacobian is not 0. See, x is not 0. Why? Because this is the region where the problem is elliptic. If x is 0, it will become a parabolic. So in that region it is parabolic. We are not interested in that. We are interested in the region where it is elliptic. So in this region, x not 0 is elliptic. So in that region, the Jacobian is also not 0. So this is a valid change of variable. Okay. So whenever you are doing some change of variable, just get it confirmed that this is a valid change of variable. Actually what happens is, you do not need to do this step. Why? Because during the canonical form, we have actually chose all of this in such a way that it becomes a valid change of variable. So you don't have to choose, show that. I am showing it to you just to confirm that this is valid. Yeah. Okay. Now what you do is this change, chain rule. If you remember, you find out what. So again, you find out what uxx, uxy. So in this case, you don't have to find uxy. You only have to find uxx and uyy and put it in the equation. So and uyy and substitute. So find these two and substitute. In terms of alpha beta, if you do that, what are you going to get? So this also I want you to check using chain rule. You are going to get u alpha alpha plus u beta beta is equals to minus 1 by 2 beta u beta. Is it okay? This is what we are going to get, and you see that this equation is nothing but a elliptic equation. Yes, again, so initially this equation was also elliptic, but the coefficient is in terms of x square, which is a much complicated equation. This is a semi-linear elliptic equation if you want to be more precise, but this equation is a purely linear equation. Yes, okay. So, and we have reduced it to a much simpler form. So this is what the canonical form is. So this is the canonical form. Okay, I hope the idea is very clear, right? Some notation, some calculations I have skipped, but it is okay. You can of course check these calculations. It's not very difficult to do. Yes. So with this I am going to end the canonical form expression. Thank you so much.